Welcome everyone. In this video lecture, we will continue our last lecture in which we had studied the two inverter bistable element behavior, okay, and some plot. So now in today video, we will think about the small signal analysis approach for this inverter based bistable element. Before that, I want to give some quick recap of this circuit. So this one is basically biastable element which consists of two inverter circuit. Okay. So in the last video lecture, we have studied the corresponding output. Okay. In which we have taken this as a say inverter 1 and 2 and this as a input say Vi1, then the output will be V01, and for this one this should be Vi2, then V02 is the output, and the corresponding response that we have already covered. Okay, this one for V01 and Vi1. Okay, inverter characteristics is the simply inverter characteristics. Okay, similarly for this here we can say V01 equals to Vi2, okay, and Vi1 equals to V02. So okay, so now V01 is same as that of Vi2. So I am writing on the y-axis, and this should be our V02. So if we plot the another one, it will go like this that we have discussed in last video lecture. So this point is our unstable point. Okay, this point we can say this point is stable. In last video lecture we have covered this one. Okay, so now in today's video we will try to think more about this one through the small signal analysis. So for the small signal analysis, what we will do, we have to consider first the inverter is in the initially at the unstable operating point. So at the one of the unstable operating point, okay, so I am saying it is at the VTH. Okay, so it will go either this side and this side. Okay, it will go up to say VOH, and the other output will be go up to V0L. So that we will try to find, okay, with time domain. So this one is some basics. So now we will go for the a small signal analysis model for this particular bistable circuitry. So for this purpose, what we have to do, again I am going to make the bistable circuit, okay, in which this one is our inverter 1, okay, and inverter 2, and we are assuming that through that inverter 1 we are giving some current Ig1, okay, and we are getting some current ID1. Okay, why I am saying in a small signal analysis, okay, I want to give some idea about the a small signal analysis. In case of a small signal analysis, for the BJT, as we know, the collector current IC equals to Gm times of VBE. Okay. Similarly, for the MOSFET, the drain current ID equals to Gm times of VGS. Okay. I'm not going to discuss more in detail, but this you have to know BJT and this one for MOSFET. Okay, and one more thing, this one having some inverter circuit. Okay, inverter circuit in which the gate of the NMOS and PMOS is connected, and we are giving some voltage, we can say H VG1, and here we can say the VG2, and this current is nothing but simply IG2, and this one will be, we are for we are doing with the a small signal analysis. So the very first thing is we have to consider the bistable circuit. This one is the bistable inverter based circuit, which is initially operating at the what unstable point. So we are saying that the initially the V note 1, V note 2 is at VTH. Okay, we have assumed. Okay, and even for our analysis, what we are assuming that the gate capacitances of each inverter. Okay, the gate capacitances. Okay, that is our CG of each inverter. Okay, capacity of CG of each inverter is is much larger than the output drain capacitances. Output capacitance. Okay, means that is our CG is much greater than CD. So this one is our assumption. What we have assumed that let let output V naught 1, V naught 2, which is shown here, is initially having VTH, which is basically the unstable point. This one is our unstable point. Okay, and we are also assuming that the gate capacitances of each inverter circuit having much higher value than the output drain capacitance. Basically, this one is somehow a inverter kind of thing. So, wait. Before analysis, I want to just give some brief. In the last video, also I have made this diagram. Okay, one inverter and one try to make one. The same inverter circuit, two inverter circuit. I am making. Say VDD, and this one is ground. Put an arrow here. Also, put in bubbles here. Okay, for this PMOS. Okay, and say this one is ours. Okay, you can put the arrow marks in some books, or they are not putting, but I am putting. Okay, so this one is our inverter number 1. Okay, this one is our okay. Okay, this one is our inverter 1, and this one is our inverter 2. Okay, and the first inverter output of the first inverter is connected to the input of the another. So output is here. So output of the first inverter, this through the drain in, is connected to the input of the other. That is our this point. Okay, similarly, the we can say the input of the second inverter is connected to the output of the, means one. Suppose this one I am saying 1. Okay, so output of this one is connected to the input. Output of 1 is connected to the input of this. Okay, and for the time being I am saying it have some capacitances value Cg. Okay, and some drain capacitances will be there. So we are assuming that the gate capacitances is much greater than Cd. Okay, so now for the SE analysis, what we are doing, we are just assuming that the Ig1 value in terms of, we are writing in terms of gate current Ig1 Id1. Okay, Ig1 means the current across the gate terminal, and we are taking output as the output current from the drain terminal Id. Okay, so from this expression one can simply write Id1 equals to our Ig2. Okay, or Id1 equals to this gate current Ig2, and Id1 is nothing but simply transconductance Id1. Okay, so Gm times of Vg1. Okay, S is grounded, so we are neglecting. Okay, now in the second one we can say Id2 is nothing but simply Ig1, but the drain current of Id2 can be written as GmVg2. Okay, this one is clear. Means Id equals to Gm times of Vgs. So Id1. So Gm transconductance, all are the mesh transistors. So transconductance is, we are assuming the same value. So Gm Vg1. Okay, Id1 and Id2. So it is equals to Ig2, Ig1. Sorry, Id2 is Ig1. Okay, so Gm times of Vg2. We can write this one. So I am assuming that this is our equation number. Okay, now next, and this one we can say that a small signal input and output currents in the inverter. This figure corresponds a small signal input and output currents of the inverter. This figure, say I'm saying this figure one or something, this figure one, this figure. Okay, a small signal input. So one expression we can write, means we are writing the inverter in terms of current. Inverter output Id1, that is our drain current. We are taking output against the drain of the inverter Id1. Okay, one inverter Ig1. So Id1 is a function of Gm times of gate voltage, so Vg1. Okay, so Gm times of Vg1. Similarly Id2 is Gm times of Vg2. Okay, here this Gm is the nothing but simply the small signal transconductance of the inverter. Gm is the transconductance of the inverter. This Gm is the transconductance of the inverter. Okay, so now after this Gm equals to transconductance of the inverter. Now one more thing, the gate voltages of both the inverters, the gate voltages, that is our Vg1, the gate voltages of the both the inverter Vg1 and Vg2. Okay, the gate voltages of both the inverter Vg1 and Vg2 can be written in terms of charge like Q1 by Cg and Q2 by Cg. Okay, the equation, because we know now fundamental equation, Q equals to Cv. So the gate voltage can be written in terms of charge Q1. Okay, the charge Q1 divided by the capacitance across the gate Cg. So Q1 by Cg and V2 equals to Q2 by Cg. Okay, so also we have to think that The small signal gate current of each inverter can be written in terms of the capacitor uh, capacitances, gate capacitances with respect to the voltage. Means if some capacitor is there, okay, to select. If some capacitor is there, I am saying this one voltage is Vg, is Cg. Okay, so the Ig1 value, the Ig1, and I am saying the current is say Ig1. So that Ig1, these three equations are very important. This Ig1 value, okay, I'm writing here, that this Ig1 value will be nothing but simply C dVg1 by dt. Okay, I am saying this one is Vg1. So because C, IC current, C dV by dt. Okay. Similarly, one more current equation we can write Ig2. The gate current of Ig2 can be written as Cg dVg2 by this one is some another expression. Okay. So now these are some equation. We can say this equation is our say equation 2 or okay this one is 3. So equation number 3, and I am saying both as a combined. So this one is our equation number 2. Both are equation number 2. Okay. So now we have some relationship between all these things. So now we have to write the equation by using anyone. Okay. So for example, Ig2 is Gm times of Vg1. Okay. So what we can write? I am saying from first equation Ig2 equals to Gm times of Vg1, and Ig2, the value of Ig2 can be written in terms of capacitances. So Ig2 can be written as gate capacitances dVg2 by dt equals to Gm Vg1. Okay, clear? Means Cg equals to Vg2 by dt equals to Gm Vg1. Okay, now again this one is one equation. Okay, similarly we can put the value of Vg, okay, or this one is our one expression. After that what we can do, Vg2 in terms of charge is there. So if we write Vg2, means first we are writing it from equation 1. This one is our equation 1. Now we have replaced Ig2 value from this one, Ig2. Okay, Ig2 here. Clear? Then after that, what we can write? Cg dVg2 by dt equals to Gm, and this Vg1 can be written as Q1 by Cg. Okay, in terms of charge we have written, so not a issue. Now again this Cg is same as that of Cg, and d by dt Vg1 we have written Q1 by Cg from this one. Okay, Vg1 Q1 by Cg. Now Cg d by d2 Vg2 is Q2 by Cg. That is our Vg2 is okay. Vg2 is Q2 by Cg equals to Gm times of Q1 Cg, or what we can write this CG cancel out. So one can write this CG cancel out. dq2 by dt equals to gm times of q1 by cg. Okay, means here we have written cg dvg2 by dt equals to gm vg1 is q1 by cg. Now vg2 is our q2 by cg, q2 by cg, then we can write this. Okay, similarly if we write another expression, similarly we have written like this. So one more equation we can write dq1 by dt gm by cg into q2. Okay, say equation number 4 and equation number 5. If we are able to write this expression, okay, if we are able to write, okay, this expression, we can also write this one. Now from these two equations we can write, if we put the value of q2 in 1, okay, we will get a expression. Now we have a quadratic in these two, 4 and 5, as a function of q1 q2 gm cg. So from equation 5, if we take the value of q2 and we have to put in this value, so from this one equation we can write like this. So another equation by the other equation, this equation ig1 equals to gm vg2, we can also write this expression. So now after that what we can write, uh, okay, from this one can write q2 equals to cg by gf dq1 by dt. Okay, then q2 is known to us. Now we have to put the value of q2. By putting the value of q2, in 4, we will make quadratic second order differential equation. Means we can write d by dt cg by gm into dq1 by dt. Okay, directly I am putting the value first. Okay, then gm q1 by cg. Okay, so if we take this cg out, cg by gm, this can be written as d2 q1 by dt square gm q1 by cg, or we can write as d2 q1 by dt equals to gm square by cg square q1, or the same equation can be written as d2 q1 by dt square. Okay, here dt square. Second order differential equation will come. I am writing q1 by t naught square, where t naught equals to cg by gm. We can write this t naught. Okay, so now this one is a second order differential equation, dq by dt square minus q1 by tau naught square, okay, equals to 0. Okay, we can write like this. Okay, I started from some equation and we have ended with some charge differential equation. Now at the end we can change this charge in terms of voltage. So after that what we can write, the second equation also one can write d2 q2 by dt square minus q2 by tau naught square equals to 0, the second equation. Now this one is our second order differential equation. Okay, so how to solve this one? So for this one, I just want to show you one concept. Minus, suppose y equals to 0. Okay, so in such equation, such differential equation, second order difference, we have to assume, then we have to find lambda e to the power lambda x, y double dash lambda square e to the power lambda x. Then we can write lambda square minus 1 equals to 0. So lambda equals to plus minus 1. Then the solution of that particular differential equation can be written as y equals to a times of lambda 1 x plus b times of 2x. So similarly, we have to do it for this one. So here q1 can be written as e to the power lambda t. So q1 dash is lambda e to the power lambda t, and q1 double dash is lambda square e to the power lambda t. Okay, now from this one we can make it lambda square minus 1 by tau naught square. Okay, after putting all these value in this one, q double dash be d2q by dt square. Okay, equals to 0 into e to power lambda t. So it should be 0. Okay, I'm writing lambda t. So now from this equation we can find the value of lambda is plus minus 1 by tau naught. Okay, so the solution for this one, q1 t will be a times of e to the power 1 by t naught into t plus b into e to the power minus 1 by t naught into t. A to the power a into e to the power t, t naught by t. Okay, clear? Okay, so in another page I will do the same thing. Okay, so we have observed first two differential equation. That once again I am writing d2q1. Okay, this one is d2q1 by dt square minus q1 by tau naught square equals to 0. Okay, and another equation we have d2q2 by dt square minus q2 by t naught square equals to 0. So if we solve this one, second order differential equation that we have solved, what we get, q1 as a function of t equals to a into e to the power what, we can say t by t naught plus b into e to the power t by t naught. Okay, that we have find. Okay, so now we have to find the value of a and b. Okay, so here we can assume that the initial condition, that q1 at time 0 equals to the get q equals to cv v g1 0. Initial condition we have been assumed. Initial condition. Okay, so that first we are doing this part. Okay, for this one we have already find. So this one is automatically we can write for this one directly the other thing. Okay, so we are not disturbing this part only. First we are concentrating, means this expression we can write from the differential equation. So now this one is one expression. Okay, so now what we can do, at at t equals to 0 we can say q1 0 equals to a e t 0, so 1 0, so a plus b. Say equation number 1, anything 1. Okay, and now this one is one expression, say capital A. So if we differentiate A. Okay, so one can write q1 dash t into 1 by T naught A. Okay, E by T naught. So 1 by T naught in the coefficient A into e to power T by T naught. Then minus 1 by T naught. So minus B by T naught. Minus B by T naught. Okay. This one is minus B by T naught minus T by T naught. Okay. Or we can write as T naught, tau naught, Q1 dash T A T by T naught at T equals to 0. Again, if we assume that at T equals to 0, the value will be tau naught Q1 0 A minus B. So this one is second equation. Okay. Now there are two equations. A plus B is this one. I am solving this one. Yeah. One expression, one A plus B equals to Q1 0. Another expression, A minus B equals to tau naught Q1 dash. Okay. So if we add these two, so what we can write? Directly we have to find A, B from these two equations. Very simple. Q1 0 plus tau naught Q1 0. Okay. Then A value will be Q1 0 plus tau naught Q1 dash 0 by 2. Okay, similarly B we can find. So I am directly writing in B we have to take it minus. So this will be cancel out. Then after B value will be simply if we take this one is minus A will be cancel out. So Q1 naught minus tau naught Q1 only minus will be there. This will be minus. Everything will be same. 2. Okay. So we have find the value of A and B. We have find the value of A and B. Okay. Now we can write the value of Q1t. So the value of Q1t can be written as Q1 0 plus tau naught Q1 dash 0 by 2 e to the power T by T naught plus B value is this one. So one can write Q1 0 tau naught Q1 dash 0. This is from Kang book. You can also follow the Kang book for more detail. Okay, but this derivation is not there, so but I am doing. Okay, this one clear. So similarly if we go for the second one Q2, okay, similarly we can write an expression for Q2. Okay, Q1 is there like this. Okay, so Q2 expression if we write for the charge in Q2 0 plus tau naught Q2 dash 0 by 2 e to the power T by T naught plus Q2 0 minus tau naught Q2 dash 0 by 2 into e to the power minus T by tau. So like that we can find, because this one is second order differential equation. If we solve for this one, it will also come Q2 dash A times of e to the power T by T naught plus B e to the power minus T by T naught. If you go and solve, it is very simple mathematical calculation. We will get this. Okay, so this one is one expression. Okay, now we can replace, as we know that the Vg1 equals to nothing but simply V02. because this inverter, once again I am making this two inverter. Okay, means this one is our, say I am saying this one is our V not 1. Okay, and this one is our V not 2. Okay, so this is our get value, get VG1 is our V naught, VG1 is V naught 2. Okay, output of this, and V naught 1 is VG2. So now we can replace the gate charges. We can replace, so basically what in the, right now we have to write in terms of voltage. So we can replace the charges, or we can say the gate the gate charges of both inverter, of both inverters with the corresponding output voltage, output voltages. Okay, so for this one VG1 we have to write it for Q1 V naught 2 and V naught 1. So simply for this one, instead of, because we know the Q equals to CV, so Q is somehow proportional to voltage, having the same proportionality, unity. We are just not considering the capacitance. So directly we can write the value of V naught 2 T will be very simple, 1 by 2 V1 naught plus tau naught V1 dash naught. Okay, clear? Okay, okay. When we are writing for V naught 2, okay, so we have to write it 2, no? Into e to the power t by t naught plus 1 by 2, and it should be our again V2 naught minus t naught V2 dash 0. Okay, divided by 2, and I put it bracket, so bracket it was minus t by. Similarly, in terms of voltage, if you have to write, okay, so you can directly write 1 by 2 V1 0 plus tau naught V1 dash 0 e to power t by t naught plus V1 naught V1 dash, okay, dash differentiation is there by 2 into e to power minus t by t naught. Okay, so after that, if we assume for large t value, for large t value, okay, for large t values, when the time is very large, t is a large value, high value. So as we know, y equals to e to the power x. If t is high, it will go, and this one y equals to e to the power minus x when t is high. So in this case, it should be 0 for t0, t infinite, or t is high, so it will approach 0 value if we plot y and x, y and x. For positive one, it will increase when time increases. Okay, but when e to the minus x, when time increases, it will decrease. Okay, so it will be cancelled for the large t values. So for the large t values, v naught to t will be simply 1 by 2 v2 naught tau naught. See, this one is the proof for this one, and v naught 1 e to power t by t naught. So this one is the voltage expression. Now this magnitude of both the output voltages, because initially we have started with a condition that both are in the unstable point, say VTH. So after that it will either go like this and this, okay, and both are connected as a inverter V not 1, so this one is V not 2. So if this one is 1, it is 0, so this will be invert, okay, for a small potential. So this will be like this and this. So it is to be clearly observed from this uh, expression, because the magnitude of both output voltages, the magnitude of both output voltages V1, V naught 1 and V naught 2 increases exponentially, okay, with time depending on the polarity of the initial small perturbation. If there is a change in dV naught 1, so I am saying change in dV naught 1 and dV naught 2, okay, a change in dV naught 1 and dV naught 2, the output voltage of both inverters will diverge, okay, to their initial value, that is unstable point VTH, to either VOH or VOL, okay. So, and one phase representation is there, means what we can say, the phase representation means if I am saying this one is V naught 2 and V naught 1, and any point I am saying this point is our the unstable point. So either it will go to this, okay, like this point I have VOH, or this VOH, okay, and this point is our VOH. So this one is our phase representation of the bistable circuit, okay. And if we find the gain, okay, if we find the gain of from these two one, so like that the gain V naught 1 at time t by V1 at time 0 is nothing but simply approximately equals to e to the power t by t naught. It is okay, V naught 1 t, V naught 1 output of the 1 with time domain with respect to V1 naught, okay, will be nearly e to the power t by t naught, okay, in a this kind of flow, you can say. Okay, so if a number of means two or more kind of this, you can say one, two inverter and another, say this one is our amplifier again, like A, okay, for second one A square to AN. This AN can be also e to power t by t naught, okay, where it also if some it have some means the unstable point, it will like same if it is considered more number of bistable element, so it will go like this. So this one is all about this theory, okay. So you can also follow the book for more details. So basically in this video I am trying to just want to solve and show the how we have to derive an expression for this one, okay. So this is all about this video lecture. So thank you for watching this video. Thank you.